This is lecture 8, and today we're going to get into some really important stuff, and it's important for a lot of reasons, and it's somewhat involved, a lot of support material behind it, and so essentially it's subroutines, and to make subroutines work right, we're actually going to use stack. Now I know people have worked with stacks before, not a big deal. We're going to look at them in depth in this lecture. So what we're interested in is program flow control, and program flow control is essentially the term that we use for the notion of that it's not the next instruction that's going to be executed. It's that the program's going to jump somewhere else and execute oh God. This is lecture number 8, and what we want to get into today is subroutines and some of the structures that support the proper operation of subroutines, which is essentially stacks. So this is going to be really long lectures. I'll break it into multiple parts here, but more importantly, get into how the RISC-V implements stacks and subroutines, and one or two examples in this. So what we're interested in is program flow control. So when we talk about subroutines, it's considered a type of program flow control because our program flow control is the notion of, instead of executing the next instruction in memory, you jump somewhere else and execute instruction. And as you know, to be able to do that, what we're going to do is load some other address into the program counter. That's going to allow us to do jumps. So what we have here is to do jumps. So once again, we have two instructions, which is these guys, and branches. We have a bunch of branch instructions. These are all program flow control. But today we're getting into subroutines, and there are actually two instructions that we'll use for this. Essentially, it's call and return, but they turn out they're actually pseudo instructions, which is good because it does a lot of the work for you and don't have to worry about the details. So namely, when I execute a call, it actually, the assembler translates it into these two instructions here, which is fine. Like I said, we can skip the ugly details for now. And these instructions are going to work because we're going to set up the hardware to make these instructions work. So this call pseudo instruction is going to work. So also there's a return pseudo instruction that is going to be simply implemented as one instruction, which is the jump and link register. And we'll talk about why that's the case in a second. So there's the hardware, and we'll come back to that. And so these are that we're doing subroutines. So what we're interested in are these two instructions. Now this is the jump and link register. So I'm going to go over these at a fairly high level to try to give you an intuitive feel for these, because this is how subroutines are implemented. Basically, this is how you call a subroutine, and this is how you return from a subroutine. And so what you see here is that anytime I do a subroutine call, anytime I do one of these instructions, the same thing happens in both of them. So this is right here, you can see that it's the address of the next instruction is going to be stored in some register. Okay, so the address of a next instruction will essentially be the instruction we come back to after we return from a subroutine. So that's the important part in this. And so what's important here also is that I can what I'm doing here is adjusting the program counter. So this is the part of the instruction that allows me to jump, and it looks kind of the same for both of them. This is the part of the instruction that allows me to return. So we'll come back to the details later, but the issue is that I can use, it turns out I can use either of these instructions to jump, but I have to use this instruction to return. And just in an intuitive sense, what's happening here, it's storing the return address in a register, and here it is. Here's that return address right here that's being put back into the program counter. So the fact that there's a register involved in adjusting the program counter means that this JALR, actually that should be an R, okay, this JALR instruction is what I'm going to use to return from subroutines. And like I said, we'll kind of work those details out in a second. So subroutines in general, the idea here is it's something you absolutely have to use when you are writing assembly code. It helps keep you organized. The code you write is going to be maintainable, reusable, and or more readable for humans as well. So here's the general idea here. This is our general program flow, and these are like chunks of code. So what you see here is these two chunks of code are exactly the same. So what I'm going to do is set it up in this fashion. So I'm going to execute A, I'm going to jump to X, execute X, jump back to B, execute B, jump back to X. So what you see here is in the end, executing these two chunks of code is exactly the same, but it's done a little bit differently. Now what I want people to understand is this code here is going to execute faster than this code, because essentially when I'm jumping around, which means I'm loading new values into the program counter, that takes up time, and that's going to essentially slow the execution down a little bit, and that's what we mean by overhead. So what you see here is this piece of code here is going to be more time efficient. It's going to run faster than this piece of code, but this piece of code over here is going to be more space efficient. So in this code, I've encoded X twice in program memory. In this code, I've only saved this X piece of code once in memory, so I can jump to it as I need to. So once again, subroutines are a great idea. It helps keep your code organized, but it does actually slow your code down a little bit. Makes your code smaller since I'm not repeating the same code twice, but once again, it slows your program down. So it's more space efficient, less time efficient to use subroutines. And it's a really important point, and we'll get back more of that in a later lecture, but I thought I would tell you now. So the subroutine usage is this is just some random code fragment. I don't even think it works, but I'm just going to have an instruction that calls. It's going to transfer program control down to this instruction here, which is associated with the junk label. We use labels a lot, not a big deal. It's going to execute this code. I don't know what the code does. It's a return. Once I hit that return, it's going to jump back to this instruction. So the mechanism is that when I do a call, I'm going to store the address of this instruction somewhere. I'm going to store it somewhere because I have to get back to that instruction. Essentially, I'm going to store it somewhere, and then I'm going to load that stored value back into the program counter once I hit that return instruction. So that's the basic mechanism. We'll see that. We'll have to understand that and implement it at low level. So let's look at that. So an intuitive approach to subroutines is the notion that I'm executing my code, I get a call, and I go somewhere else. And I go somewhere else by loading the address of some other instruction into the program counter. But at the same time, when I do that call, I have to remember where I need to come back to. So I'm storing the return address somewhere. So that's the interesting part, where I store it. Okay, so when I hit that return from our subroutine, so program control returns to that instruction that I stored. I'm done with the subroutine. It takes that stored address, which is the address of the instruction after the call. It puts that address into the program counter, which gets me back to where I need to be. Now the issue is where am I going to store that return address? So pretty much automatically, it's automatically stored and register X1. Register X1 has an alternative name, which is RA. Everyone knows that as short for return address. So the notion here is when I do a call, the return address is stored in X1. When I do a return, it loads X1 back into the program counter. Okay, and there's going to be some issues with that are going to come up, and we'll look at those issues as they come up. Like, well, here they are. The issues have come up. Essentially, call and return, they work great, but there's only one X1. So if anytime you have a subroutine that calls another subroutine, you actually have to store that X1 somewhere, which is the return address. And so the notion here is when you have nested subroutines, you generally need a place to store a register value. And so that's what we'll talk about next. Is generally speaking, in microcontrollers such as this, we always need a place to store data when we need to store data, and that place is going to be on the stack. And I believe that's going to be the next slide here, which is stack. So I'm going to go ahead and stop that here, call it done for this lecture, and we will jump back at this point on the next lecture.